So it's been said that this homework lesson is a little challenging, so thought I'd give you guys a homework help video. I'm not going to do all the problems. Some of them I feel like are exactly like what we did in class. For those, I'm just going to ask you to look at your notes. But the ones that I will be helping you guys out with today are 21b, 40, and number 20 is really tough. So don't feel bad if you didn't get that one. But once I show you how to do it, learn something from it. All right. So here we go. Let's go ahead and take a look at number 21b. It says, consider the triangle formed by the side of a house, the ladder, and ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet away from the wall. There's also some other information at the top of that problem, in case you guys didn't notice. It says that the ladder is 25 feet long. It says that it's being moved away from the wall at a rate of 2 feet per second. And what else does it say? I think that kind of covers it there. All right. So they want to know about the area, but let's go ahead and just follow our steps. So I've got my picture here, right? We have the height of the ladder and we have the base of the ladder. So what rate am I trying to find? I'm looking for the rate of change of the area, right? An area is always going to be in square units. So what are our measurements here? We're dealing with feet. So the final answer is going to be in square feet per second. Let's go ahead and take a look at number 2. What rate is given? They've given us the rate of change of the base of the ladder. They've told us that it's a positive 2 feet per second. It's positive because B is growing if they're pulling the base away from the wall. Number 3, we're going to go ahead and find the formula that relates area to the base of this ladder. So the formula that relates the area of a triangle to its base is 1/2 base times height. Okay. All right. Now that's going to be an interesting formula to find the area for. Because it's got a product in there. So when we take the derivative, we're going to have to apply the, guess what? The product rule. Okay, so let's go ahead and do step 4. We take that derivative. It's going to be the derivative of the area with respect to time is equal to 1/2 b times the derivative of the height, which is dh dt, plus 1/2 the derivative of the base times h. Okay, now I could write this a little bit different so it looks a little bit more familiar to you guys, but if I wrote it like this, maybe it would make more sense to you if you're not already seeing it. You guys remember that? That's the product rule, right? So that's all I did there. I had to do the product rule because I have 2 variables that are being multiplied together. All right, so let's go ahead and continue working this out here. Now's our time to go ahead and start plugging stuff in. Well, I know what B is. They tell us that B is 7, right? I don't know the rate of change of the height yet. I'm going to have to probably figure that out in a second. Plus 1/2 dB dt. We do know that. It's 2. And the height, I don't know that either. Okay? But that is what's going to give me the rate of change of the area with respect to time. All right. Well, let's start with something easy. We can find that missing height pretty easily using the Pythagorean Theorem, right? Now, usually when we go back to the original formula, right? But this formula is not going to help us find the height. because all we know is the base, but I don't know the area, and I also don't know the height. You can't solve an equation with two unknowns. But if I use the Pythagorean theorem, I can solve for h, right? Pretty sure I've solved this out quite a few times, and every time it keeps coming out to be 24 if I'm not mistaken. So h is 24. Now the next thing that's kind of tricky here is the whole dh dt thing. How in the heck are we going to find dh dt? Well, this would be a tough problem if we were coming at it blind, but actually just look back at part A. In part A, didn't we find dh dt, how quickly it's moving down the wall whenever the base was 7 feet, which is what we're looking at, isn't it? Aren't we looking at when the base was 7? So look back at 21, part A. What did you get for dh dt, the rate at which it's sliding down the wall, when the base was 7? So if you did it correctly, by the way, the answer is in the back of the book, it was negative 7 over 12 feet per second. Well, from there, you would just go ahead and do all your math and work it out. I think I'm going to go ahead and let you guys do that part. That's pretty easy. But just don't forget your units, which is square feet per second. Okay? All right. So let's go ahead and move along here. So that's number 21, part B. Let's go ahead and take a look at number 40 now. All right, in number 40, we have a little bit of a challenge. They don't give us the picture this time, so we kind of got to draw our own picture. A balloon rises at a rate of 4 meters per second from a point on the ground that's 50 meters from an observer. Okay, so we have some observer here, right? And this dude or dudette is 50 meters away from this balloon that started here and it's going up. Now, I don't know how high it is at the moment, but I do know that it's moving at a rate of 4 meters per second. Let's go ahead and continue reading here. Find the rate of change of the angle of elevation of the balloon from the observer when the balloon is 50 meters above ground. So I'm looking for the angle of elevation. So this one is just like what we did in class, but this one is also a little tricky. And so I would hope that you guys have at least tried this problem before you start watching me do this using your notes, because watching me do another problem is going to help you at this point. You've seen how to do it. Now it's your turn to practice. But if you tried it and you're just not getting it, I will gladly share with you how to do it. So let's do that. So we do have a changing value. The 50 is not changing, so I'm going to put 50 there. But the height of the balloon is changing, so I'm going to put an h there. All right, and what this piece here represents is that represents the rate of change of the height, right? It's positive because the balloon is going up in the air. There's my balloon. All right. So what am I trying to find? I am trying to find the rate of change of the angle, which of course we talked about in classes in radians per second. It was seconds, wasn't it? Let me double check. Yeah. Okay. Next, they give us a rate, and the rate that they give us is dh dt. And that rate is 4 meters per second, and it's a positive because the balloon is going up. Now, what formula would relate these two things? Now, your hint is it also has to include this. Well, we talked about it. You're going to use the SOHCAHTOA formulas. This angle is going to be there, obviously, but these two sides are opposite and adjacent. The trigonometric formula that connects opposite and adjacent is tangent. So tangent of theta is equal to h over 50. Okay, that's our formula. Now we're going to take the derivative of it. Tangent of theta is secant squared theta. Now I'm going to write it a little bit different just so my math is a little bit easier to follow for you guys. We also need to take the derivative of this side, once again, remember that this is just really 1 over 50 times h, right? So I encouraged you guys to consider writing that a little bit differently in class because it just makes it easy for people to see how to do it. So the derivative of 1 over 50h is 1 over 50, but since h is not a function of, it is a function of time, we've got to do dh dt. Oh, and I forgot my d theta dt over here, didn't I? Bad, Mr. Bailey. All right, so let's go ahead and plug in what we know. Well, the one thing that I do know here is I know the dh dt. dh dt is 4 feet per second. Obviously, I don't know d theta dt because that's what I want, the rate of change of the angle. Another thing that I don't know yet is what is secant theta, but we talked about how to do that in class. Secant theta, hopefully you remember from your trigonometry class, is hypotenuse over adjacent. Now, I know what the adjacent is. The adjacent is 50, but I don't know the hypotenuse yet. But that's not a problem because I can find it. Now, it says that we are concerned with the moment in time when the height of the balloon is 50. So I'm going to go ahead and put a 50 here now. And what we would do is we would use, you could use Pythagorean's theorem if you want to. I guess I'll put, yeah, I can leave it as C. But you know what, you guys? If you also are kind of sharp and you remember your geometry, this is an isosceles triangle that's a right triangle. And when you have that, the hypotenuse is always whatever the sides are multiplied by radical 2. That's a 45, 45, 90 right triangle. Now, if you don't want to do it that way and you want to do it with Pythagorean theorem, you'll still get the same answer in decimal form. But I'm going to go ahead and save myself the time and just put 50 radical. All right, so if that's my 50 radical 2, then that's what the hypotenuse is. That's what's going to go here. So secant of theta is 50 radical 2 over 50, which reduces to just being radical 2. And that's what I'm going to go ahead and plug in over here for my secant. Now, radical 2 to the second power is simply 2. 4 times 1 over 50 is 4 over 50, which if you reduce it is 2 over 25. And then finally, last step is we're going to divide both sides by 2, or just so it's more visually appealing, since we're working with fractions, I'm going to multiply by the reciprocal, which makes these 2's go away. And now I'm left with the rate of change of theta with respect to time is 1/25 radians per second. Okay? So there's that. Now we're going to go ahead and move on to number 20. Number 20 is an interesting question. So let's jump right in. All right, so on number 20, I'm going to go ahead and draw the picture on here. Something like this. You guys are impressed with my art skills, aren't you? All right. Tells us that this distance here from the top of the triangle to the bottom of the triangle is a total of 3 feet. It tells us that this length back here is 12 feet. And it tells us that this upper rim is 3 feet. What else does it tell us? It says it's an isosceles triangle, so these sides are equal in length. What else? What else? What else? What else? All right. So part A of this question tells us water is being pumped into the trough at 2 cubic feet per minute. How fast is the water level rising when the depth h is 1 foot? Okay. Well, I guess I can get fancy here and creative and put some water in here, huh? There we go. All right. So h is the height, right? And that is this length right here. Now, there's a couple of things that make this hard, this problem. The first thing that's hard is the formula. I didn't give you guys any formula for this particular shape, okay? So you kind of have to know some geometry here. This is a triangular prism. The way that you find the volume of a triangular prism is you find the area of the triangle face here and you multiply it by the length of that shape, and that gives you the total volume of that figure. Okay, so that's one thing you guys are going to have to know how to do, is how to find the volume of a triangular prism. There's another little thing that's hard along the way. You'll kind of see it. I'll make mention of it when we get there. And then a third thing actually just occurred to me is another geometry fact that you have to be aware of. This little triangle right here that represents, you know, the triangle of the water, right? That triangle is similar to the big triangle, okay? Now what's interesting about that is that you'll notice that since the height of the big triangle is 3 and the base is 3, well, since this little triangle down here is similar to it, guess what? Its base and height will also be equal to each other, okay? So there's all the stuff that we kind of need to know, and we'll go ahead and work through this and see what shakes loose. So part A, what rate am I trying to find? Well, I want to find the rate at which this water level is rising. Now that's the height of this little triangle. So I'm looking for the rate of change of the height of that little triangle. And height is going to be measured in linear units of feet per, was it second? Let me take a peek. Minute. All right, so next we have the given rate. The given rate is the rate of change of the volume. And they've kind of given that to us in a kind of a sneaky way. That's just how fast the water's pouring in. So they tell us that the water is being pumped into the trough at 2 cubic feet per minute. Now that's the rate of change of the volume, so we'll say dV dt. Now I need a formula that is going to be relating the height with the volume. And so now we come to one of our first big challenges here on this problem. And that challenge is that we need to know how to find the volume of a, what did we say this was? A triangular prism. So like I mentioned, the area of the prism, I'm sorry, the volume of the prism, I'll put V prism, is equal to the area of the triangle multiplied by the length of that triangle. Length. All right. So I'll just put V now. The area of the triangle, as you guys know, is 1/2 base times height. The length of this figure is 12. Now notice that I put a 12 in and I didn't put L, but here I put letters. Why is that? Well, let me ask you, in this entire problem, does the length change? No. The length is always 12 all the way up. But this base and this height are constantly changing. They're both increasing. Okay? So there's our formula. But now, I guess we could simplify this a little bit. 1/2 times 12 is 6. So now here is your volume of the triangular prism. But we're going to go a little bit further. There's nothing wrong with having that B in there. But a little, I mean, we could actually probably do this the same way that we did the last problem, actually, where you just use the product rule. But do you guys want a little bit of an easier approach? It requires a little twist, which isn't obvious, but if you want an easier approach, check this out. Didn't I say earlier that the base of this triangle and the height of this triangle is the same, and since this one is similar to it, its base and height would also have to be congruent? Well, what that means is that B equals H, right? And since I want a formula that relates V and H, I really don't need the B. So what I can do is I can replace that B with another H because, as I said, B equals H. A little bit of a trick there, but there's nothing wrong with opening our mind to new thoughts. That's what school's all about, right? So here's our volume of our cylinder. Now that little trick I just showed you is something that we're going to do next class, actually. We're going to come across problems that have more than one independent variable, and we're going to have to substitute it out, right? So there's that. So now we're going to go ahead and move on to part D. Now once we've gotten past all that, the rest of this problem is a breeze. But the hard thing was the geometry, figuring out the volume and getting that formula down. All right, so dV dt is equal to 12h times dH dt. And my goal is I want to find dH dt. So let's go ahead and move on to step E here. dV dt we said was 2. H was given at a value of 1. So that's going to be 12, and then we just divide both sides by 12, and we get 1/6. So there you have it. The rate of change of the height is 1 foot per minute. I'm sorry, 1/6 of a foot per minute. Okay, so that's number 20. 20 part A anyway. Let's take a look at 20 part B. Now it tells us that the water is rising at a rate of 3/8 of an inch per minute. Now, notice what they did here. They just changed it to inches. Now that's kind of important. You don't want to overlook that. They're talking about inches now instead of feet. So they're telling us now that the height is rising at 3/8 of an inch per minute when h equals 2. Determine the rate at which the water is being pumped into the trough. So now we have to understand we're not pumping water into the trough at 2 cubic feet per minute anymore. What we're noticing now is we're just looking at this trough. We could see that the height has an increase, a rate of increase at 3/8 of an inch per minute, and we want to find out how quick is water going in. So the picture's the same, so I'm going to skip step 1. But I'm going to go ahead and move on to step 2, which is identifying what rate we want to find. This time they want to know how fast is water filling it up. In other words, they want to know what's the rate of change of the volume. So now we want to find that, which is in cubic feet per minute. C, on this one, they're telling us what dH dt is, how quickly the water is rising. However, at this step, I'm going to do something a little bit unforeseen and unexpected. But once again, open your minds and let it soak in and grow a new nerve or neuron in your brain so you can learn something new. We want it to be in feet per minute, but as you notice from the problem, they gave it to us in inches per minute. Okay, how do we turn inches into feet? Well, let's start with something simple. Suppose I had 24 inches. How would you turn that into feet? Well, Mr. Bailey, you divide it by 12, you'd say. And I'd say, hey, good job, that's 2 feet. But then if I said, how many feet is 3/8 of an inch, you're all of a sudden going to get confused. But just remember, if it worked for 24 inches, it's going to work for 3/8 of an inch also. So in other words, I need to divide 3/8 by 12. And doing a little bit of basic math here, same change, flip, reduce, we end up with 1/32 of a foot. So if the water is increasing at 3/8 of an inch per minute, then that means it's increasing at 1/32 of a foot per minute. So I converted the units. Notice that little strategy too. The fraction confused me, so I started with something that didn't confuse me, and I used that process to derive what to do with the one that did. It's a good math strategy. Soak it in and use it. There you go. Part D, we're going to use the same formula. We're still relating volume to height, so I'm still going to say volume is equal to 6h squared. E, the derivative will remain the same. dV dt is equal to 12 h dH dt. On this one, I don't know dV dt, but I do know h. In the problem, they tell me that h is 2, I believe. And they also tell us what dH dt is. It's 1/32. So now we just get to simplify this and see what's up. So that's going to be 24/32, which reduces by 8 to be 3/4 of a foot, cubic foot, right, per minute. All right, so if you watched this, you got a nice little sneak preview into the kinds of problems we're going to do on Monday. All right, guys, hope you're loving it as much as me. I love this stuff. I think it's cool. Anyway, we'll see you on Monday, and have a good weekend.